Section: Introduction. In this section, we introduce prediction markets, which are platforms that pay out based on the occurrence of specific events. For instance, a market might offer $1 if Jeb Bush is elected president in 2028, with the price indicating the market's estimate of that event's probability. These markets are valuable for gathering diverse information to form accurate beliefs. Historically, large language model (LLM) forecasters have not performed as well as human forecasters, but recent studies suggest that LLMs can now compete with human predictions on platforms like Metaculus and Predictit. A crucial question arises: how do we evaluate LLM predictions once they surpass human performance? Long-term forecasting is particularly challenging because it's hard to determine the truth of events that will unfold far in the future. One proposed method is to assess the logical consistency of LLM predictions, even if we can't verify their accuracy. For example, if an LLM assigns probabilities of 0.5 and 0.7 to the events of Trump being elected and someone else being elected, this creates a logical inconsistency. Previous work has shown that models like GPT-4 and GPT-3.5 Turbo can fail basic logical consistency checks. Our contributions in this paper include: 1. We establish principled metrics for measuring consistency in binary forecasts, introducing a theoretical framework that includes an arbitrage metric and a frequentist metric. We apply these to 10 logical consistency rules. 2. We present a consistency evaluation pipeline for LLM forecasters, creating 2 datasets with known outcomes, one from prediction markets and another generated from news articles. These datasets focus on events occurring after the training data cutoff for the forecasters we evaluate. 3. We find that our consistency metrics correlate with the actual forecasting performance of the models, regardless of the time frame. While backtesting is an option, it can be difficult due to unclear training data and the emergence of new question types. We explore whether consistency metrics can predict future performance. 4. We discover that increasing computational resources can enhance consistency for some logical checks, but this improvement does not generalize well. We developed an arbitrage forecaster that adjusts a base forecaster's outputs by generating related questions, but this approach only improves consistency for specific checks without enhancing overall forecasting performance. 5. Finally, we create a long-horizon benchmark consisting of 3,000 consistency checks for forecasts that will resolve in 2028. This benchmark covers various topics and serves as a testing ground for advanced LLM forecasters. We also provide the code and datasets used in our research. Section Summary. In this section, we discuss the development of metrics and a pipeline for evaluating the logical consistency of LLM forecasters' predictions, particularly in long-term forecasting where ground truth is often unavailable. We demonstrate that our consistency metrics correlate with forecasting performance and introduce a long-horizon benchmark for testing advanced LLM forecasters. Section: A theoretical framework for forecasting consistency. In this section, we present a theoretical framework for assessing forecasting consistency. We denote the set of forecasting questions we are interested in as a specific group, and the possible outcomes for each question as another group. Our focus is on binary forecasting questions. A forecaster can be seen as a mapping of these questions to their outcomes. One important forecaster is the ground truth, which assigns a probability of 1 to the true outcome and 0 to the false one. For questions that can have conditional outcomes, we also consider optional resolutions. We define consistency checks as pairs of relations in the question and forecast spaces, along with a condition that must hold true for all feasible forecasts. If this condition is violated, we measure the inconsistency using specific metrics. For instance, the negation check involves certain relations on questions and forecasts. We provide a complete list of the consistency checks we utilize in the appendix. We improve upon previous work by deriving our metrics in a systematic way, allowing us to handle various logical consistency checks at once. We introduce 2 new metrics, the arbitrage metric and the frequentist metric, which help us measure logical inconsistency in probabilistic forecasts. The arbitrage metric represents the minimum guaranteed profit an arbitrager can achieve by betting against the forecaster's predictions. If the forecaster's probabilities are inconsistent, there are prices that the arbitrager can set to ensure a profit regardless of the outcome. We define the maximum guaranteed profit that can be achieved by selecting the right prices. We also identify the set of prices that maximize this minimum profit. A more detailed version of this metric, along with examples, is available in the appendix. The frequentist metric, on the other hand, is based on sampling from a world model. It measures how many standard deviations a forecast is from the mean of the Monte Carlo forecast, scaled to be independent of the number of samples. We consider a consistency violation to occur if the forecast deviates significantly from the mean. Our metrics tackle two main challenges in measuring inconsistency. They are tolerant to noise and allow for principled aggregation of inconsistency scores. In traditional Bayesian settings, beliefs are either consistent or not, but in practice, forecasts often show some level of inconsistency. Our metrics provide a smoother increase in inconsistency rather than a binary measure. Additionally, we ensure that all consistency scores can be compared and aggregated meaningfully. For example, in the arbitrage metric, we sum the profits made by an arbitrager across different questions to assess overall inconsistency. Section Summary. In this section, we present a theoretical framework for assessing the consistency of binary forecasting questions, introducing two new metrics: the arbitrage metric, which quantifies potential profit from betting against inconsistent predictions, and the frequentist metric, which measures deviations from a Monte Carlo forecast. Our approach enhances the evaluation of forecasting consistency by allowing for smooth gradations of inconsistency and principled aggregation of scores across different checks. Section: Pipeline Overview. In this section, we outline the steps in our data collection pipeline and provide further details on each step. We begin by preparing datasets of base questions through various methods: scraping questions from online platforms like Manifold and Metaculus, creating a resolved dataset from news articles, and generating synthetic questions on topics such as politics, science, and economics. For the first two methods, we also include the correct answers for each question, which we discuss in more detail later. Next, we transform the base questions into tuples that must meet specific consistency checks. For instance, each base question is turned into a tuple, and pairs of related questions are also formed into tuples. We then query a forecaster to obtain predictions for each question, resulting in forecast tuples that should maintain consistency if the forecaster is reliable. We evaluate each tuple of forecasts for consistency using our violation metrics, and we provide examples of data at each step in the appendix. The prompts and calls to the language model used before forecasting are also detailed there. When generating forecasting questions, each question includes a title, a detailed body with resolution criteria, a resolution date, and optional metadata. We scrape questions from Metaculus and Manifold markets, focusing on those that resolved between May 1, 2024, and August 15, 2024. This process yields over 500 questions, with 242 passing our verification step. To create forecasting questions from News API articles, we concentrate on articles about specific events rather than opinions. To avoid bias towards positive outcomes, we modify key entities in the questions while keeping the overall theme intact. We verify each question's correct resolution using the Perplexity API, achieving a less than 5% error rate. We compile 2,621 resolved forecasting questions for the period between July 1, 2024, and August 21, 2024, using a subset of 1,000 to explore the link between consistency violations and accuracy. For synthetic question generation, we use few-shot prompting, sampling 6 examples of forecasting questions and relevant tags to diversify our output. We generate titles, remove duplicates, and then create the question body and resolution date using a language model, resulting in 1,000 forecasting questions that resolve by or in 2028. Throughout these steps, we filter generated questions using a language model to check for coherence, clarity, and relevance to real-world events. Questions that do not meet these criteria are discarded. We also gather human feedback to refine our prompts and examples, with an example of the feedback form included in the appendix. Finally, we use the Bayes forecasting questions to create tuples of logically related questions. For example, pairs of Bayes questions can generate tuples for logical operations like and or but. The main content of these questions is generated synthetically, while resolution dates and other properties are calculated systematically. We ensure the correctness and relevance of the tuples through scoring and verification that they describe logically related events. Section Summary. In this section, we outline our data collection pipeline, which involves preparing datasets of forecasting questions through scraping, synthetic generation, and verification processes. We ensure the consistency and logical relevance of these questions by instantiating them into tuples and applying various checks, while also incorporating human feedback to refine our generated content. Section: Relevance Scoring. In this section, we focus on relevance scoring. When we combine Bayes questions into tuples, we must avoid questions that are unrelated, such as asking if SpaceX will be worth $200 billion by 2030 based on Sri Lanka's rice production growing by 40% by 2040. For tuples made from multiple Bayes questions, we evaluate 2,000 possible combinations by their relevance score, which we obtain by querying a language model to assess how relevant the questions are to each other. We then select the top 200 combinations for each consistency check. Next, we verify the tuples by passing them to another language model to ensure they fit the intended structure. For instance, we check if the resolution criteria of the second question truly negates those of the first. We provide examples of these verification prompts in the appendix. We also test various forecasters using different language model versions, including GPT-4o and others, with and without chain-of-thought prompting. We run these forecasters on a total of 5,000 tuples, using a mix of questions from scraped sources and News API, except for one model that we test on only 50 tuples per check due to cost limitations. Some forecasters could not be tested because of API changes. In our results, we evaluate the forecasters based on consistency and the Breyer score, which measures forecasting accuracy. We note that a model's Breyer score can be influenced by its training data cutoff, meaning a stronger model might score worse if its data is older. We exclude any forecasters with a Breyer score worse than random guessing to avoid skewing our analysis. We find a strong correlation between average consistency scores and forecasting performance. By aggregating consistency scores across checks, we can plot the average Breyer score against these scores. Our findings suggest that Bayesian consistency checks are the best indicators of forecasting performance. We observe a strong link between certain consistency checks and average Breyer scores, indicating that tracking logical consistency in conditional probabilities can serve as a proxy for overall accuracy. However, not all consistency metrics correlate well with forecasting performance. We see that some checks provide clearer signals about actual performance than others, and combining different metrics seems to enhance correlation. We acknowledge that our selection of forecasters is limited, so we cannot ensure these trends will hold for future models. Part of the correlation may stem from better models being both more consistent and more accurate. For comparison, we note the correlations between our forecasters' Breyer scores and error rates from a benchmark dataset. We include all relevant data in the supplementary material. Even strong reasoning models show inconsistencies. We present the full set of consistency metrics for one of the best models, highlighting how often it violates consistency checks. Finally, we create a dataset of 900 synthetic questions with resolutions set for 2028, generating 3,000 tuples to evaluate forecasters over longer time horizons where ground truth is unavailable. This dataset serves as a prototype for ongoing long-term forecasting benchmarks. Section Summary. In this section, we outline our approach to relevance scoring for question tuples, ensuring they are contextually appropriate, and describe our verification process to maintain structural integrity between questions. We evaluate various forecasters on their consistency and forecasting accuracy using Breyer scores, revealing that Bayesian consistency checks serve as effective proxies for forecasting performance, even in the absence of ground truth resolutions for long-term predictions. Section: Arbitrage Forecaster. Can we design a more consistent forecaster? In this section, we explore the concept of the arbitrage forecaster, aiming to create a more consistent forecasting model. We start with a question tuple for consistency checks and analyze forecasts to maximize an arbitrage metric. This involves generating improved forecasts that are consistent and determining the profit an arbitrager would make by betting on these forecasts compared to the original ones. We then consider whether we can use these improved forecasts to develop a new forecaster that builds on a base model but offers greater consistency. We introduce the arbitrage forecaster, which uses the base model and checks for consistency. It works by creating a tuple that meets the consistency criteria, querying the base model for forecasts, and then adjusting these forecasts based on the arbitrage process. However, we note that the arbitrage forecaster is not inherently consistent by definition. Its consistency must be tested through empirical methods. For instance, if a forecaster generates certain forecasts, the resulting forecasts may not always align consistently. We provide a detailed definition of the arbitrage forecaster in the appendix, including how it can be applied to multiple checks and a theoretical discussion on its consistency. We highlight strong theoretical reasons to expect that using recursive setups of the arbitrage forecaster could enhance consistency, particularly with certain checks like negation. Due to the complexity and costs associated with running these recursive models, we focused on a limited number of setups and checks. Our experiments show promising results. Arbitraging on a check improves consistency for that check, with deeper recursive setups yielding greater consistency gains. Notably, this improvement also holds when arbitraging across multiple checks. We found that the greatest consistency gains occurred with negation, followed by paraphrase, and the least with expevidence. While we did not observe significant improvements in overall forecasting performance or consistency checks outside those we focused on, our findings align with our hypothesis that the arbitrage forecaster is particularly effective with symmetric and deterministic checks. We also discuss related work on metamorphic and consistency checks, noting their historical use in various fields, including machine learning and large language models. The challenges of evaluating superhuman AI performance without ground truth are acknowledged, and we emphasize the role of consistency checks in scalable oversight and model evaluation. Section Summary. In this section, we introduce the arbitrage forecaster, which aims to enhance the consistency of forecasts by arbitraging them against specific consistency checks. Our preliminary experiments suggest that this approach can improve consistency, particularly with symmetric checks like negation and paraphrase, although we do not observe reliable improvements in overall forecasting performance. Section: Contributions. In this section, we outline our contributions. We developed consistency checks and metrics for arbitrage and frequentist analysis. Our team, including DP, AA, APS, and EU, worked on the evaluation pipeline for the LLM question. APS conceived and implemented the arbitrage forecaster. VB was responsible for creating the dataset of questions derived from news. AS and DP compiled the dataset of scraped questions, while A and DP generated the synthetic question dataset for 2028. DP initiated and led the project, with FT suggesting a correlation between consistency and forecasting accuracy, providing valuable guidance. All authors contributed to the writing process, with DP and APS drafting the initial version of the paper.